Hello, my name is Pawel Moll, and I'm a programmer by trade, but have deep interest in performance analysis, and therefore will try to show how to employ power of statistics to do that. Because any decent presentation in 21st century must begin with a quote, I looked for one describing performance analysis, and I found one on English Institute of Sport website. I must say, I find it weirdly accurate looking through my own experience. So from now on, I will consider myself a program coach. Now, in the far history of computer science, performance analysis was a rather laborious matter. I can vividly remember my father spending hours over dot matrix printouts of assembly code with a red pen, annotating program flow with processor cycle cost of instructions. Or it would be at least instrumenting code with log messages and other annotations impacting program behavior. Things have started changing when processor architects at DEC decided to add a small processor block. Since then, known under many names, I'll use one, performance monitoring unit, and essentially it comprised a few counters connected to processor clock, instruction execution unit, etc. And for a small cost, with virtually no overhead in runtime, it allowed to calculate simple metrics. About some of them I'll talk about later, but it all allowed us to systematically observe program behavior. And let me add that when I had an opportunity to personally meet one of the alpha team, Dick Sides, I thanked him for this. This was one of the best things that happened since the invention of bread. So this presentation will revolve around using statistical methods in different forms, some less orthodox, to analyze the behavior of a particular workload running on AWS Graviton 2 platform, powered by ARM Neo version 1 processor. It will take us through three stages: workload characterization, trends analysis, and effect cause correlation. Each stage, each one digging deeper. I should probably start with describing what this workload is. So it is a real-life digital verification test bench, something that our silicon designers, this was about 10 years ago, created and spent countless hours and billions of CPU cycles running to make sure our venerable Cortex-A53 processor behaves as it should. So let me emphasize, in this workload, I will be simulating Cortex-A53 running on Neo version 1. So it is generations ahead, but those are far relatives. And this test bench comprises 114 unique tests executed in 5 different processor configurations. So in total, we are getting 570 data points. And each data point is statistically relevant. Here it comes, the statistics already here, as each data point is a mean of 12 independent runs in controlled conditions, and each is tested against the standard deviation for the results. So I'm pretty confident that the results are meaningful. What is also worth emphasizing is that in this particular case, we are looking at a single tool exercised from different angles. So there is one particular tool that is being executed in different conditions. This makes this case slightly different than the typical academic research on performance analysis, which often focuses on spec-like benchmarking suites designed to cover many different types of workloads, each with specific dataset. Now, the EDA tool being used is Mentor's QuestaSim, and I worked closely with Mentor engineering team porting this tool to ARM architecture to make sure it behaves as good as possible on our platform. This presentation is a result of a performance analysis workshop we've organized, which resulted in a number of optimization kind of suggestions that they are working on currently. But that's a subject for another, probably more than one presentation. As I mentioned, I'm a programmer and honestly know very little about digital verification and EDA tools. I knew even less when I started that. So I wanted to start with characterizing the workload, to look what it looks like. And in order to do that, I wanted to capture basic metrics using standard Linux perf tool. Here we can see how to do this on a very simple example of a bubble sort program. Just in the base case scenario with data already sorted, this particular code needed 14 million cycles and 42 million instructions to finish. Now, the best case scenario for bubble sort, no data is all already sorted. It just means follow through the code and finish it. The worst case scenario, where the data is reversely ordered, raised these numbers dramatically. So it was 83 billion instructions to finish. Now, let's call it average or average case with just random data, input data, brings this number slightly down, number of instructions required slightly down to 67 billion instructions. So all is fine, right? But wait, there's one interesting thing here. It's fewer instructions, 67 versus 83 billion, but more processor cycles. So I had 83 billion instructions executed in 27 billion cycles, but 67 billion instructions, 16 billion fewer, take 31, so 4 billion cycles more. Why? That seems wrong, right? At the first sight. Branch misprediction is the obvious culprit, but we'll get to this later. For now, let me just draw your attention to the right of the screen, the instruction per cycle metric, pointing at 304 and 215. We'll get back to this later. And now getting back to the workload, the EDA workload I started talking about, here is a chart showing number of cycles, that's the left y-axis, to finish each individual simulation, that's x-axis here. And just for future, to make it clear, I will use lines instead of individual dots, but keep in mind we are talking discrete results here, not continuous data. And the other thing worth noting from this chart is that the simulation that is longest takes more than 15 times more time to finish than the shortest one. So clearly there is a wide variety of behavior here. And indeed, if we look at the number of instructions on the same chart and number of instructions that required to finish the workload, then we will see that it is not exactly, generally speaking, it goes up together with number of cycles, but it's not directly proportional. There are dramatic differences. And now remember the instruction per cycle metric I mentioned. Modern processors can execute more than one instruction each processor cycle. In particular, they can issue more than one each cycle, and this issue stage determines theoretical maximum of IPC, of instruction per cycle. In case of N1 in Graviton 2, Neoverse N1 in Graviton 2, it could be 4 in ideal scenario. Now, remember the bubble sort example? It was 3 in the kind of good case versus 2.15 in the worst case. For the EDA workload, the matter look even worse. So the IPC almost never goes over 1. And it's also very noisy. You can see it from the chart. Plotting IPC on such a chart pretty much didn't help me at all to understand what was it like. So the next step I've done was plotting it a slightly different way. So instead of getting a number per simulation, I've plotted each individual data point on cycles versus instruction axis. So the gray line in the diagonal gray line is IPC1. Okay. And in this shape, in this form of a chart, we can start seeing certain regularities. When I started looking at this plot, kind of in an interactive way, at each individual data point individually, I spotted certain regularity. Some of the names of the tests had one thing more. Applying a linear regression, that would be the next step I wanted to do, to this data didn't particularly help me in any particular way. You can see that the additional dotted line, which is a result of a linear regression of this data, is kind of aligned with one of the groups, but not the other. So it's like averaging the noisy chart before. It doesn't actually help. But as I say, I looked at each individual point separately and noticed that some of the names of the tests had a dynamic term in it, and others didn't. So the other ones were static. Explanation later, but it started making sense from that moment on. I realized that I had to treat those two categories of tests separately, and running linear regression on those two groups separately also show much better alignment with the data, and pinpoints clear outliers in static tests and dynamic ones as well. Such outliers are always good candidates to start looking at in detail. With this knowledge, I moved to look at trends. First of all, I've consulted digital verification experts to understand what the difference between static and dynamic tests are. It turns out that the simulation tool will execute two distinct types of code. RTL, so the language that silicon is described with, translated into native instructions. In case of Questa, this will be a JIT engine doing the translation. And the second category is a statically compiled test data generators and test constraint checkers. Static tests will generate the test data and constraints in the initial phase and then focus on RTL, on JITed RTL, while dynamic tests will interleave these two phases continuously. The first question I wanted to answer then was, so how much time the individual tests spend in JITed code? And sample-based profiling was the tool to get the answer. The principle used by many profilers like ARM Streamline tool or the Linux perf tool I've already mentioned, the principle is pretty simple. So use PMU or a timer to generate periodic interrupt, for example, by overflowing a PMU cycle counter. When the interrupt gets handled, check what instruction it was being executed before the interrupt was handled, record its address. In a way, it is similar to analog to digital conversion. So if the process is relatively periodic and the sampling frequency is large enough, we will get a statistically relevant picture of code behavior, particularly hotspots. The gathered samples are then resolved against debug information and grouped into functions, showed how much time each function contributes to the program execution time. Because JITed or runtime generated code doesn't have such information normally available, those samples would be treated individually. Now, fortunately, the Linux perf tool takes custom symbol maps. So allows us to generate a simple text file describing the memory area where the JITed code, the generated code would live, and attribute it to a single JIT symbol. And this gives us pretty much a percentage of the participation of the JIT code in the total runtime. And indeed, static tests spend almost 2 more time cycles in JITed code than the dynamic ones. So the next question, obviously, is how does the amount of JIT code executed relate to the overall system behavior? And the answer is very obviously visible on the chart. Percentage of JIT code goes up. That's the right y-axis. Number of instruction, the blue line, left y-axis goes down. Okay. Therefore, IPC goes down as well, and the code behaves worse. Ergo, the JIT code generator is an area for improvement, except that for the outlier cases that we have identified earlier, remember the IPC chart? This relation doesn't happen. So again, we have two subcases here to separate, to analyze separately. So the next question will be, so why exactly the number of instruction is going down? What is going on? And to drill further, it is good to start from looking at certain PMU events, which can be grouped into two sets, front-end and back-end stalls. And there are events, PMU events, available to measure those. So let's have a look at the correlation between branch misprediction, which causes pipeline flash, that's the orange dotted line, and front-end stalled numbers. It couldn't be clearer. There's a clear correlation here. Front end of the processor, so you can think of it as the left-hand side of the pipeline drawing, is responsible for fetching, decoding, and issuing instructions. And suddenly, when a branch misprediction and pipeline flash happens, it suddenly doesn't have anything to do because it lost all the instructions in flight. So it has to start from scratch. In other words, it is stalled. Similarly, the instruction cache introduces pipeline introduce pipeline bubbles, where new instructions are not dispatched for a few cycles as they haven't been fetched in time. On the other end, in the back end of the processor, so where the instructions are being actually executed, any data cache miss will cause backend stall. Load store units in the back end of the processor are a finite resource, and when they are all occupied waiting for data from the main memory, no new load store instruction can be executed. And again, there is a clear correlation between the data cache happening and the backend stalls line going up as well. So if we plot the 3 events count on one chart, the chart gets busier, but we can start spotting some correlations even manually. Like the greenish dotted line, where instruction cache misses go down, are usually corresponded to the instructions, the blue line, instruction number going up. Okay, fewer is the fewer instruction cache misses, the better the code behaves, the more efficient the code execution is. Here we can see a dramatic example of correlation between poor data cache utilization and IPC going down. Okay, and this is the outlier in the dynamic test that we have identified before. But now, but we can, instead of looking at the picture, we can use the power of statistics again and to see which one of the events are the most interesting ones. So Pearson correlation coefficient calculated for the selected hardware performance events against number of cycles show that the data cache, L1D cache refill event, and branch misprediction, BR mispred events are of much higher interest, 0.96 and 0.94 correlation than all the other ones. Now the Pierce coefficient itself, the definition of it, it can be pretty much derived from these pictures. On the right-hand side of the screen, you see the kind of mathematical extreme definition of it. So high coefficient means very organized data, pretty much in a single line, while random cloudy data means a lower coefficient, kind of there's a randomness inside the data, and you can see it from the data on the chart as well. The numbers captured from the PMU event by PMU for the iCache misses are much wider distributed, so the coefficient is lower than the data side. Now, if we now know what to look for, we can get to the last phase, and we can try finding the culprit, the particular instruction causing, for example, branch misprediction. I have focused here on branch misprediction because of many things, but in particular because we have realized that the workload is memory bound anyway, so improving anything on the data side would be more difficult than looking at the branch misprediction. It was just a choice of the two top events, and we went with the branch misprediction first. So let's start doing this. in order to do so, will try using the same principle as the sampled profile mentioned before, but we have to work around a specific problem. We could try configuring PMU as a source of the sampling period tick. You remember sampling profiler? You take a PC program counter, you take addresses of instruction on some events at some period of time and try to draw a picture out of it. We could try configuring the PMU as a source of the sampling period tick, but to use, instead of CPU cycles, the branch mispredicted event, right? That's simple. Let's try doing this. So branch gets executed, right? The counter is incremented. That will cause an interrupt being generated, which will go through the interrupt controller. Now the problem is that the instructions, while this is happening, the instruction CPU is still executing instructions. So it moved on from the branch instruction and is now doing something else. And by the time the interrupt is being handled by the processor, and we have an opportunity to check the program counter to see the instruction of an address of an instruction that was executed a moment ago, it is something different. It is, for example, in this particular case, you can see it on the perf tool screenshots there as well. It is compare. So compare instruction cannot really generate a branch mispredicted event, right? Now, the distance between the instruction happening and in the moment when we take the observation is called a skid, and it can be significant, and what even worse, it is unpredictable. But here's where statistical profiling extension come to the rescue. It is ARM architecture extension that appeared in version 8.2, and it is now available in Neoverse N1. And to kind of cut the long story short, it is a hardware implementation of a sample profiler. It behaves more or less the same way as we have discussed before. It just, because it's implemented on the hardware side and it's very closely integrated with the processor pipeline, it allows us to observe many more information and in much greater detail than previously. It does require some support from the operating system, so there is slight overhead, but it is pretty hard to measure, really. And when it comes to Linux kernel, the support is available there in version 4.14. So let's have a look at the bubble sort example that we've seen before with the SP enabled. So we will use the perf tool as previously, but a slightly different command line argument, but in principle, we will get to the same situation. Program counter branch instruction is being executed. Program counter points at the branch. SPE, so the Statistical Profiling Extension hardware, is configured to look for branches. So what will happen next is that the SPE will create a sample record at the moment when the instruction was executed, taking its program counter, number of information about the processor. You can see it in the decoded information from perf. There is a type of instruction that is a conditional branch. There are some information about latencies, which can be later used for other purposes. And this record will be then stored in the main system memory. So that's where the overhead comes from. The SPE will take some small portion of the interconnect of the memory system to store those records in the memory. What happens later is that the offline, the execution has stopped. The SPE data has been stored on storage, and offline perf tool at the time of writing it required some additional patches, but it has been now merged, so basic functionality is already available in mainline kernel. It will use these records to synthesize events. So, for example, if we ask it to synthesize events for branch misprediction situations, it will create samples. Then, as you can see in the screenshot, points exactly at the branch instruction that is in bubble sort main loop. So we can see here on the simple example that it will pinpoint the culprit. Now, applying the same logic to the big EDA workload that I was talking about revealed 3 particularly hot areas of code, with one standing out. And that's where the mentor engineers have focused their attention for the time being. So this brings us to the end of the very quick ride over statistics and performance analysis. Just to summarize, we have shown how me, so a software engineer who didn't have any knowledge, or at least very little knowledge of what a workload looked like, how it behaved, and what it was supposed to do, without having even access to the source code, I was able to analyze the behavior and pinpoint at least 4 or 5 different categories, different areas of potential improvements that are now being worked on by our partners in Mentor. Thank you very much for your attention, and we will try to answer some questions in the chat now.